Hi there, welcome to the Retro Desk. I'm Matt Heffernan. This is the first episode of a new series that seeks to demystify assembly language programming for the 6502 processor family, and specifically for the 65C02 found in the Commander X16. I made a version of this series before using the X16 emulator, but now the real system is available and we will go through the entire development process, from coding to running on hardware. In my engagement with the retro computing community, I have seen a lot of trepidation when it comes to making the leap from high-level languages like BASIC down to the computer's native language of ones and zeros, expressed as assembly language. This series will assume that you already have some familiarity with programming in a high-level language, and some rudimentary understanding of things like hexadecimal numbers and Boolean logic. If you don't, I would recommend checking out my series on Python programming for beginners, and I have some additional resources linked at my GitHub repo page that's linked in the description below. So what exactly is assembly language? Every processor has one, after all, each used to various degrees by different kinds of programmers, but mostly by those that need to have low-level control over the hardware or have tight performance constraints. An assembly language can be defined as a human-readable set of mnemonics that represents a processor's machine language. But what's a machine language? That's the binary code that a processor executes from memory. So that means that an assembly language program directly represents the ones and zeros that go into the processor and tell it what to do. While languages like C or Pascal can be compiled into machine code, the result of that compilation depends on how their compilers are implemented. When you write a line of code in C, you don't know exactly what machine code that is going to translate into. You can even compile that code for completely different processors like ARM or x86 and get completely different code. But assembly languages are for specific processors and cannot be simply assembled into machine code for different processor families. Different processor models within a processor family may have compatibility between them, with certain models having unique instruction mnemonics, but generally have a lowest common denominator of machine language that can be executed by all models within the family and use consistent assembly mnemonics for them. This lets us use the same assembler program to assemble code for multiple processor models within the same family. An assembler is a program, like a compiler, that takes in an assembly program text file and outputs binary machine code. That program may run on the platform you are programming for, but quite often it is on an entirely different and more advanced machine. In that case, you would use a cross-assembler. Since it's just translating the mnemonics into ones and zeros, it doesn't matter what kind of computer is doing it. Assembly is usually a fairly quick process, but later in this series we will look at ways it can be more complicated. For this series, we are going to use the CA65 assembler, which is part of the open-source CC65 toolchain. It can run on just about any modern platform, but will only generate machine code for the MOS Technologies 6502 family processors, including the 65C02 that the X16 uses, as well as the 6507 in the Atari 2600, the 6510 in the Commodore 64, and even the 65-816 hybrid 8-16-bit processor used by the Super Nintendo. There are several other 6502 assemblers out there, and they have different syntaxes for some things, but the instruction mnemonics are the same across almost all of them to comply with the original MOS standard used in assemblers going back to the birth of the 6502 family in the mid-1970s. The 6502 and its variants have an extremely simple architecture, mostly to keep its cost down. It predates the modern concept of a reduced instruction set computer, or RISC, but by necessity has a very small set of instructions anyway. It is an 8-bit processor and really commits to the concept by having only 8-bit registers, with the exception of its program counter, which is 16 bits by necessity of the chip having 16-bit addressing. If you have seen any of my Atari 2600 videos, however, you may remember that the 6507 only has 13-bit addressing to even further reduce cost. But as far as the actual machine language goes, addresses are still 16 bits wide. The register that can be used in the most ways is A, also known as the accumulator. It is the only register that can do any sort of math other than incrementing or decrementing. Most data in any program has to pass through A to be used for anything. Instructions that use A are either loading a value into it, modifying it, or storing its value in another register or memory address. Then there are the index registers, X and Y. You can load and store values to and from them and increment and decrement them, but that's it. Their primary use is for indexing through arrays in memory. There are certain addressing modes that only work with one of them, and we'll be getting into that in detail in a later video. The other register you have to be generally aware of when programming is the status register, also known as SR or P for processor status, depending on context. You don't actually use it as an 8-bit value. In fact, only 7 bits are used on most chips in the family. Rather, you deal with each bit independently, as they are all status flags that have certain meanings and behaviors. That will also be in another video. The other registers are more or less dealt with automatically in most programs. I've already mentioned the program counter, or PC, which keeps track of the memory address of the current instruction to run. The processor automatically updates the program counter after executing each instruction, which will either change to the next instruction in memory or jump to a different part of memory depending on the instruction and its result. Finally, there is the stack pointer, SP, or simply S for short, which is actually only 8 bits, as the memory stack must be contained in a single 256-byte page of memory, starting at hex 100. This is one of the many limiting factors of 6502 software, and a big reason why assembly language is the best option for serious development on platforms in this family. Like all conventional computers, the 6502 executes code as a series of instructions in memory. Like all microprocessors from the 8-bit generation, it can only execute one instruction at a time, and then move on to the next instruction based on the address in the program counter after the last instruction was executed. 6502 instructions are between 1 and 3 bytes, with the first byte being the operation code, or opcode for short. Each opcode has a fixed number of bytes that will immediately follow it in memory that the processor will need to read in order to execute the instruction. Instructions that only consist of the opcode are also known as implicit, meaning they have no operand in the code that affects its behavior. Other opcodes will have the processor do something with those 1 or 2 bytes following it. 1-byte operands are going to be either immediate 8-bit values or addresses from the 0 page, that is, the first 256 bytes of memory space, where the upper 8 bits of the address are all 0. The 6502 can use the 0 page for special purposes that often require fewer cycles to execute than accessing data from a full 16-bit address. 2-byte operands are always addresses above the 0 page that the instruction is either loading data from or storing data to. The 6502 assembly mnemonics simplify the specification of these opcodes by using the same 3-letter instruction abbreviation for opcodes that do the same sort of operation. For instance, all instructions that load a value into A use the LDA abbreviation, but that could be translated to any of the 8 different opcodes that load A with some value using different addressing modes. This is where the operand syntax comes in. The assembler will be able to determine the opcode to use based on the syntax it sees following the instruction name. If you have no operand after LDA, the assembler will fail and report an error that you specified an invalid addressing mode. And that's correct. LDA can't be used implicitly. It has no meaning to simply load A. Load A with what? You need to have an operand that is formatted using the correct syntax for your intended addressing mode. The assembler will then be able to match the mnemonic of your assembly language instruction to the correct opcode and then the correct 1 or 2 byte operand to complete the machine language instruction. Here we see the instruction LDA-1, which means to load the immediate value of 1 into A. This will be translated to the hexadecimal bytes A901. A9, or in binary 10101001, is the opcode for the immediate addressing mode for LDA. This will always be followed with a single byte containing the value to load, in this case 1. Before assembly languages, instructions like this would be made in punch cards, sometimes requiring the programmer to punch out every single bit, or it could be run in real time by flipping switches attached to the data bus and clocking in the instruction 1 byte at a time. Assembly language mnemonics make it much easier to program without having to memorize all the different opcodes or have to format all the operands in binary. You only have to remember the instruction abbreviations and then the addressing modes that are available to them, which generally makes sense. Certain processors in the 6502 family have additional instructions and special addressing modes for common instructions representing all the different available opcodes, and those can be remembered fairly easily. But a good reference is absolutely necessary to have handy. You can find some at the GitHub repo link in the description. Now let's finish this program by doing something with this new value in the accumulator. At this point we could do some math, adding or subtracting some value from memory, or maybe shifting the bits in the register or doing some sort of Boolean arithmetic, like a bitwise AND or OR with some value. But in this case we will do the simplest math operation we can do on the 6502, incrementing. Note that other processors like the original 6502 or the 6507 don't support this with the accumulator. For those you need to add 1, which requires a lot more memory and time. But for the 65C02 we can just use the INC instruction without an operand, which translates to the hex opcode 1A, which is not a valid opcode on the original 6502. If you were to execute that on a processor that doesn't support it, the behavior may not be defined, and it could cause the program to crash. However, the X16 has the 65C02, so it will simply increment A, changing its value to 2. No memory access is required for this, so it's pretty fast and only took up a single byte of code. Now that we have this new calculated value, we need to do something with it. In this case, we are going to write it to a location in random access memory, or RAM, meaning we can write to it from our program and read it back anytime later. Here we are using the hex address 1000, which would be the same as decimal 4096, or 4 kilobytes from the top of memory. This part of memory space is available as RAM on the X16, but not necessarily on all 6502 family systems. That address may also contain executable code, in which case writing there would be bad in general. I am certainly not covering self-modifying code in this episode. But in our case, we are going to be placing this code where it can be run from the basic prompt, meaning that hex 1000 is going to be way past the executable part of our code. We'll see how that works shortly. So to write this value to RAM, we use the instructions STA $1000. STA is short for store A, and in this case we are using a direct address, so it will be translated to the opcode 8D. You see that we denote a hex value in our operand with a $. This could have been done without the $sign by using the decimal address of 4096. But generally, we use hex for addresses as it makes it easier to see what page of memory it is in. In this case, we are writing to the very top of the hex 10 page, or the 16th page past the 0 page. If you want to use binary for operands, you could use the % symbol instead of the $sign. But that gets a bit absurd for 16-bit addresses. You could absolutely write this instruction as STA %0001, then 12 zeros if you really wanted. But generally, binary is only used for immediate 8-bit values. You will also notice that the STA operand doesn't have a hash symbol like the LDA instruction. This is because we are using the direct addressing mode, and the hash denotes the immediate mode. STA doesn't support the immediate mode because it makes no sense. You can't store a value to another value. It needs to be stored to a location. So any operand for STA has to resolve to some sort of address. For direct addresses, the syntax is just the address, in whatever base you want to use in your assembly code, which usually means hex, thus only a $sign. However, simply having a direct address is not enough to determine which opcode is used. The 6502 has different opcodes for direct addresses for the 0 page and the rest of memory. As hex 1000 is not on the 0 page, the hex 8D opcode is used, followed by the 16-bit address. Since the 6502 family is little endian, more on that in another episode, the bytes of the address are reversed in the instruction from what you'd expect. So the complete hex machine code instruction is 8D0010. If we stored the value to a 0-page address, we could use the hex A5 opcode followed by the 1-byte address. This would appear in code as something like STA $10 and translate to hex A510. No high byte for the address required, as it is implicitly 0. Because it has one less address byte to load at runtime, the 0-page instruction executes faster, which may be desirable for tight performance. Phew, that was a lot. I know that seemed like a big fire hose of information to explain a simple 3-instruction, 6-byte program. But this is the basis for all assembly programming. You need to keep track of what is being stored in the accumulator at all times and making sure that the value is stored where it needs to go once it is finally calculated. We'll get into how you use the index registers and the different addressing modes to accomplish this in later episodes. But for now, let's get this program ready to run. Here we see our code in a text editor. I prefer to use VS Codium, but you can use any editor you want, even VI or Notepad if that's how you roll. Immediately you should notice that there's a bunch of stuff on top and another instruction below our code. If you saw my Hello CC65 video, you will recognize the stuff on top. This is the boilerplate required by CA65 to make a program executable from the basic prompt. First, we need to specify our starting address, which is hex 080D. This is a special magic address on the X16. Okay, it's not really magic, but it seems like it until you understand what's going on. When you link your program with CL65, it actually creates a file that is loaded to hex address 0801 and puts some seemingly random bytes before the start of your machine code. This is tokenized basic for sys 2061, plus 3 bytes of zeroed out padding, and then your machine code actually starts, which will end up at hex 080D, which is 2061 in decimal. So we have to start with .org $080D, which will make our code start there. Then we have to make sure we define all the required segments that are in the default X16 configuration for CA65. All of them have default starting addresses, except for once. So we just make that one start right along with our code. Then you will see a label followed by a colon, start. This isn't really necessary, but it's nice to have a label that you can reference later in the code that points to the beginning of execution. We'll get into labels more in later episodes, so for now, let's see how our code looks. The general style for CA65 is to have instructions indented by 3 spaces, and labels to be at the start of the line. This isn't a strict requirement, but it is easy on the eyes, especially once you have a lot of labels and loops and data and stuff. But here we just have the code, those 3 instructions we already went over, followed by a new one, RTS. That is short for return from subroutine, which is translated to the hex 60 opcode. When the basic interpreter does a sys call, it will return to the basic prompt when it encounters an RTS that resets the program counter to the basic interpreter code in ROM. That ROM address will actually be placed on the stack, so the RTS will make the processor pull that address off the stack and put it back into the program counter, and control is relinquished to basic. Of course, you can define your own subroutines in assembly and grow the stack so that an RTS will go back to your code and keep your program running, but that will be in another episode. For now, let's go ahead and run this program. First, we need to build it. We need to have a PRG file for the executable program to load from BASIC, and it would also be nice to have a machine code listing to help with debugging. So we are going to use the CC65 linker, CL65. I already have all the CC65 toolchain binaries in my path, so I can just call it right from the directory where I have my code. If you don't have CC65 installed like this, check out the instructions that I have on GitHub linked in the description. So the arguments I need for CL65 are first to specify the target system, which I do with -T CX16, which means that the assembler and linker will use the default configuration for the Commander X16. It also supports many other targets like the Commodore 64 and the Nintendo Entertainment System, and will make sure that you are only using opcodes that are supported for that system's processor. If I were to use INC without an operand for a C64 program, the assembler would have an error, as the implied accumulator addressing mode is not supported for INC on the 6510. The next arguments we need are to specify our desired artifacts. First is the PRG file, which I can do with -o space example.prg, which means that our main output file will be called example.prg. As I am running Linux, I need to make sure that my file names that I'll be using with the X16 emulator are in all caps. Then I specify my machine code listing with -l example.list. Now the rest of the arguments can be a list of assembly language files, but I only have one. Load store.asm. I like to use the .asm extension for assembly source, but you can use .s or whatever you like. So I'll let this run, and you see that it finishes almost immediately. This is a pretty small program, and I am assembling it on a very fast modern computer. Having a lot of code and linking individually built files can make assembly and linkage take an appreciable amount of time, but rarely more than a few seconds on a modern computer. If we do a directory listing, we can see the two new artifacts we specified. First, we'll take a look at the listing. Here we can see the machine language program starting at hex 080D, like we specified in the source code, and then the starting address for each instruction and the hex opcodes and operands we were expecting. In between the addresses and machine code, you will see a column of ones. This is the include depth, and we will get into that in another episode. For now, we aren't using any include files, so our depth is always 1. Now let's take a look at the actual PRG file that we are going to load. The first 2 bytes are the load address, which is also little endian. So starting with hex 0108 means that the data starting from the 3rd byte will be loaded into RAM starting at hex 0801. Then you see 0B08. This is another little endian address, hex 080B, which is where the next basic instruction would be placed in RAM. But we don't have another basic instruction, just our machine code. So it ends up just pointing to those 3 zeros of padding, which indicates the end of a basic program. Moving on, we have hex 1302, which is another little endian value, but this time for the line number, which is 531, or hex 0213. Then we see hex 9E, which is the token code for sys, which helps to make the tokenized BASIC more compact than writing out SYS and then parsing it out at runtime. Then we have the argument to sys, which is Petsky encoded decimal number 2061, also known as hex 080D. And that's it for the tokenized BASIC. As we'll see, this should generate a listing of 531 sys 2061, but our machine code is nowhere to be seen in that listing. It's hidden at hex 080D, where the BASIC interpreter can't see it. So in our PRG, we see that padding and then the same machine code we saw in the listing, starting with A901 for our LDA #1 and ending with hex 60 for our RTS. And that's it, a whopping 21-byte file that will load 19 bytes to RAM and execute 7 bytes of machine code. Now let's get that running in our emulator. We're going to call it, again, I have that binary in my path too, and I have instructions linked in the description to help you with that, with the -debug option, which will enable the built-in debugger. This will let us see our code in place in RAM and visualize the state of the memory before and after the program is run. Now we can load our program from the host file system with a simple load example.prg. And that will put the file payload into memory at hex address 0801 as expected. We can verify that by hitting the F12 key to open the debugger. Here we can see the current state of the processor registers and disassembly of the currently executing code with the instruction at the program counter address at the very top. We can see here that we are up in the read-only memory, or ROM portion of the X16 memory space, executing the basic interpreter. It is simply waiting for us to type in another basic command, but first let's poke around some more in the debugger. Typing a D for disassembly followed by a hex address will change the disassembly window to start at a different address. And in this case, we want to start a machine code at 080D. Now we can see our original assembly disassembled using the same mnemonics we used to write them in the first place. You will notice that the INC instruction uses a slightly different syntax, explicitly making A the operand instead of an address. But we can't see the machine code itself, so let's go ahead and dump the raw memory below. We can do that by typing an M for memory, followed by a hex address to start the dump window from. We'll go with 0800 so that we can see the tokenized basic 2 starting at 0801. And there it is, just like we saw in our host terminal, but now actually in the emulator RAM at its intended address. The basic interpreter expects the current basic program to start at 0801, and our program then executes machine code at decimal 2061, or hex 080D. Now let's check out the memory our code will modify at hex 1000. Here we can see that this part of memory is just random garbage. Our program should change that first byte of garbage to a 2. So let's go back to the basic prompt and test it. We can do that by hitting the F5 key. Okay, now let's run our program. We could do the sys2061 ourselves, but as we can see with a quick list command, that the current basic program is just going to do that anyway. So we just run it. Well, that was fairly uneventful. Did it work? Let's check the debugger to see. Hitting the F12 key again shows that our memory dump window still starts at hex 1000, and now that 2 is right where it's supposed to be. To verify it more conventionally, we can go back to basic with F5 and peek at the address. With a single print command, we can show that the value is indeed 2, which is luckily the same in decimal and hex, making this hand verification much easier. Now, if you have an actual Commander X16, you can try running this program on real hardware. First, we need to copy example PRG to an SD card. We'll pull the card out of our X16 and place it in our computer's SD card slot. If you don't have a slot already, you can buy a USB card reader for less than the cost of a decent card. Now we just copy that PRG file right to the root of the card so that it's easy to load. Then we pull the card out and put it back into the rear slot of the X16 and power it on. Just like with the emulator, we can load example.prg and list the program. Still has that same sys line, so we know that the same code has been loaded into memory. Before we run it, let's take a peek at address 1000. Okay, some random value. Now let's run the program. And then we can do another peek. And see that it's now 2, as expected. We just ran our own assembly code on a real 65C02. So that's as far as we're going today. I hope you found this informative and useful, and not too much to take all at once. As you can see, when you get right down to the code, it's not very complicated. You just need to acquaint yourself with the mechanics of writing, assembling, loading, and running the program. We could have done the same thing in BASIC with a simple poke $1000,2 command. But then what? Well, we will see in later episodes how programming an assembly language can open up a whole world of possibility with the X16, as well as other retro systems. If you don't want to miss the next episode, please make sure you are subscribed to my channel and click that bell to get notified of when any of my videos come out. Please check out the repo I have for this tutorial on GitHub linked in the description and give it a try yourself. I promise you it's not that painful. At the repo link you will find more links for further reading to help expand on some of the concepts I touched on here. If you want to support my channel further, you can click the join button to become a channel member, or join our Patreon community, like the folks you see here. Either way, you will have ad-free access to all of my videos before they are available for the general public. Thanks for watching, and I will talk to you again very soon. Bye-bye.